Hi everyone, my name is Chacha, and today I'm going to be talking about enzyme kinematics, something that I didn't really touch on in my last video about enzymes just because this is sort of like such a beast of a topic, and it's so important on the MCAT that it deserves its own video. You will most likely see one or two questions in the biochemistry section for this. Um, but before we get into like the more nitty-gritty about the Michaelis-Menten and Lindweaver-Burke, we should probably talk about the lock and key method, active site and allosteric site, and induced fit model for enzymes. So what is the lock and key? So it's a perfect match for the substrate. And essentially saying that your substrates and your enzyme are soulmates in a way. Perfect pair, invisible string, whatever you want to call about it. So I like to sort of think about it because I just like pant sizes, I guess. So it's size specific. So size 4 jeans, think about it, right? Like you won't fit into a 0 or an 8. You have to be a size 4 to sit into a size 4 pair of pants. And that's sort of the same thing. So you have your substrate and it binds into the active site. So the active site is just like that opening where the substrate binds to the enzyme. Um, and it's a perfect shape. See, like the circle, and this is more of a circular active site. So it's perfect. So it's like one on one. Like only that enzyme can bind. Sorry, only that substrate can bind to that specific enzyme. And then you have the allosteric site, which is here. That's just like another place where an inhibitor or another molecule can bind to the enzyme, change its shape or its function. Um, yeah, so we'll get more into that about inhibitors since there's a well, non-competitive inhibitor will bind to the allosteric site, whereas a competitive will bind here, and then there's uncompetitive, which is just mixed, and we'll learn more about that since uncompetitive is something else. Um, then you have the induced fit model. So, you kind of the enzyme, usually it's enzyme, it's not more or less the substrate that has to compromise in order for them to bind together. So this is kind of like one size fits most. It's what I like to think about. It's like if you have like pant sizes again, back to that analogy, you have small, medium, and large. So like if you have a small pant, then it's like a lot of people like let's say it's like size like 0 to size 2 or 4 can sit into small, and then it's like medium, it's like size like 6 to like a size 10, large is like 10 plus. So it's sort of like that. So it's like more broad, but there's still like, for example, like if you're a size large, you can't fit into that size small. For example. Like there's still some limitations, but it's more lax. Um, so basically the enzyme, you can see here that the active site is more circular and the substrate is more square. This is like kind of an extreme example, just to get the point across. Usually there's some subtle differences um between the active site and the square and the substrate. Like, but this is just more or less to get the point across. So like this weird thing definitely won't fit into that more circular active site. But like see like once the substrate comes closer and this starts to like covalently bond or try and like bind bind to the enzyme in the active site, um it'll start changing shape. So you can see that now it's more square here, whereas this is more circular or like concave shape. So that's kind of the two theories. They're kind of like running their theories, right? So it's like there's some evidence to support it, some that disproves it. Those are kind of the two ones that you need to know for the MCAT. Also, we should probably talk about cofactors and coenzymes. So I like to think about a cofactor sort of like a toupee or something that like makes the enzyme in the active site more attractive to that substrate. So it's like kind of like, or I guess you could think of someone wearing like a lot of makeup too. Um, so it just makes it more attractive, more likely to bind, better fit overall. So both parties are equally happy. Sort of catfishing, but not really. So, for example, like I still have that more circular active site here, but this is that green little thing here. This is my little cofactor friend, and it can go into that active site, and it can kind of be its wingman, and then that substrate finds it a lot more attractive. So now it can bind happily. See, it's more square now, so it's a better fit. Um, Yeah, it allows for better binding. It's typically an inorganic metal. Since like they help balance the charge as well. Which makes sense just because metals are better at handling charge than non-metals. Um, like they can disperse the charge more evenly throughout, whereas non-metals can't. So that's more of a chemistry concept that I'll probably talk about in the future. Then you have a coenzyme. These are water soluble. Typically they're inorganic. Um, or not inorganic. So yeah, typically not inorganic, but they're water soluble compounds. Typically they can be like pretty large. And it makes sense that they're water soluble just because you don't want to have like a chaperone for like enzymes and substrates just because they're typically in the blood, which is more hydrophilic. And hydrophilic compounds are water loving, hydro meaning water, philic meaning like loving. It's in the name. Um, just because you want the enzyme to be as more efficient as possible, and you don't essentially want it to be like dead weight and have and have the body spend more energy on carrying around the coenzyme. And the coenzymes, they transfer electrons. So they're sort of like an oxidoreductase, but oxidoreductases are actually enzymes themselves. Um, this is not. So like most enzymes are proteins. That's also something to keep in mind. So these aren't proteins themselves. They're just little helpers. Coenzymes and cofactors are little helpers. Um, yeah, also it's really important when you're like thinking about like the rules of like like chemical reactions. So like number one, like the moles have to be balanced. And number two is the charge has to be balanced. So that's why a lot of the times, like for cofactors, they're really important in glycolysis, or gluconeogenesis, and like all of those like biochemical pathways. They're just really important for making sure that there's balance, since you can't have that energy disparity because just disparities in general. Otherwise, the reactions won't occur since it's impossible. You can't just lose energy out of the middle of nowhere. That just could just have something and be like, oops, I forgot. That's just lazy. That's like lazy script. It's like a plot hole. Sorry, you can think about it like that. Um, okay, now let's get into the main entree. That was a little appetizer. Now we're talking about enzyme kinetics. So we have our beautiful Michaelis Menten and Lynn Weaver graph. So Michaelis Menten, so on this y-axis is velocity, and velocity is related to Vmax. So Vmax is just like the maximum rates. So like the absolute maximum rate that the enzyme, like their chemical reaction can occur in your body. Then your Km is essentially one half of that Vmax. So it's like the substrate concentration. So it's one half of that Vmax and how much substrate it's needed to get to that one half of Vmax. Um, so Km is like a measure of like how efficient or like how like likely like binding affinity, sorry, like words. But the binding affinity of the enzyme substrate. So like the less substrate you need to reach one half Vmax is better it is, right? Since it's a more efficient and your body is all about saving energy and efficiency. So like the more left towards the graph, so like the smaller the KM, the better, the more efficient. So you want small. Don't want large. Large is not good. No, large. Whereas that Vmax is sort of what I was talking about. It's the maximum rate of the enzymatic reaction where there is unlimited substrate. So like if there's just like substrate falling from the sky, it's like your body like can be as saturated as possible with it without dying, since your body is like a flower. It's like literally anything will kill it if everything is out of whack. Um, and yeah, and when that substrate is bound to said enzyme, so it's a theoretical limit. This is also why we have that like one half Vmax of Km, because this is a lot more achievable than the actual Vmax. You're a lot more likely to see Km or one half of that Vmax in nature, whereas the Vmax, just because it's a theoretical value, is like really, really unlikely to occur. And then you have the Lineweaver-Burke graph. So this is also called the double reciprocal graph. Whereas like you see here, I forgot to say this is like a log function graph, right? You see, oh, it's like starting to level out, like reaches asymptote. Whereas this is just that y equals mx plus b, so it's really easy. It's just like linear. It's whereas this is a lot harder to read than the Lineweaver-Burke. And you don't really need to know the equations behind these two graphs. It's just there's a lot going into it, and the MCAT isn't really interested in your knowledge about it. It's more of like the application and understanding like broader concepts. So this is not really math heavy since you don't get a calculator. So, um, only small mercies in life with the test makers. Also, if I were to see something like that on the MCAT, I would probably cry myself to sleep, but that's okay. Um, it's the same thing. So like what inverse, right? So, inverse is like 1 over that integer. So it's the same thing. So, your X and Y values are the same, or like oh my gosh, units are the same. So it's 1 over v for your velocity. So instead of like having that Vmax be that y-intercept, it's now y over, oh, sorry, 1 over Vmax. And then on your x-axis, instead of having that substrate competition concentration, it's 1 over that substrate concentration. And then you have your -1 over km, and then I'll explain why it's negative in a minute. Um, Whereas the positive values are over here. So yeah. So why do we have this? So the negatives will cancel out, eventually leaving a positive km. That's why like it's -1 over km. So like think about it, right? So you have -1 over km equals that negative integer. So like when you like do them like really simple math, simple algebra, right? If you follow along, you have like -1 over km equals -5. Yada yada, -5 over km, and then these negatives, right? So like if you multiply or if multiply or divide a negative by a negative, it's a positive. So they cancel out. So the km is actually 1/5 over km. And remember, right? Um, the larger the km value is, the less efficient it is. So you want smaller kms. So like for example, if this was like -10, then that's a more efficient enzyme. So like you want it to be. Most inhibitors, we'll get to this in a second, but yeah, uh, it's just more efficient. Um, yeah, like over here, for example, it's like that -10. So like, right, so this is 0.2 versus 0.1. So this one, the where the x-intercept is -10. Since the k -1 over km is always your x-intercept, and your 1 over Vmax is always your y-intercept, right? Sort of like you could see here, like that's the x-intercept, this y-intercept. Um, so like this would be a more efficient enzyme, or like I guess like enzyme substrate complex. Um, okay, so now let's talk about competitive inhibitors. So now we're getting into the three main type of inhibitors that you'll see on the MCAT. So same thing, velocity and substrate concentration will always be your y and x-axis respectively. So competitive inhibitors, they will only change your Km. They will not change your Vmax. And here I have a little explanation as to why, and then we could get more into the graphs. So your competitive inhibitors, it'll bind to the active site. So like that site where the substrate and the enzyme directly meets. So it's not the allosteric site, which is kind of like the sneaky trap door in a way. So it directly competes with the substrate to bind to the enzyme. So this is why the Km is higher for the inhibitor, just because you need more in order to reach that 1/2 value. However, like a substrate, the inhibitor can unbind. So that means the Vmax will be the same. Because if you theoretically have an infinite amount of that substrate, then it's going to outcompete the inhibitor eventually. So you'll reach that Vmax value. And this is why the Vmax is the same. So here, right? Like this is more left shifted, so it's like a smaller km, where so that means that the this is just like the enzyme substrate, and this is like the dotted line with the eye with the dark green, that's your inhibitor. So then you have your km, it's more right shifted, so it's bigger, so less efficient. So you need more substrate in order to reach 1/2 that Vmax. Um, Whereas with the Lineweaver-Burke, same thing. You can see that the y-intercept or the Vmax is the same thing. And then their KMs are different. So yeah, that's what I was like talking about with the over here, like with the -5 as the x-intercept versus the -10 as the x-intercept. Um, if you have like a more positive value. So like this, for example, the inhibitor would be the -5. Just think about this as the inhibitor. And then you can think about this as like, I'll just call it regular because that negative, so this is more efficient since you need, remember, like the smaller your KM, the better. So this is a smaller value than the inhibitor is. Just because remember, like you need less substrate in order to reach that Vmax or half of that Vmax. And that is why. So it's kind of a little bit of a mind trip. Just think about it, right? Like, yeah, just like really, hey, like I need like less substrate in order to reach like the same value. So it's more efficient. Just think about it like that and you should be fine. It's kind of the opposite of what you would expect, which can be a little mind trip. Now let's talk about non-competitive inhibitors. So first I'll do the same thing where I have like the Michaelis-Menten plot and then I have the Lineweaver-Burke. But first let me talk a little bit about like what the heck is happening. And then here I have a little explanation for the Vmax as well. With like the inverse, this is the same thing, but instead the Vmax, you want the higher the better. Which is like the same thing for um all of the graphs, like just like Vmax in general, like you want it higher, whereas Km you want it to be like as low as possible, is more efficient. So the inhibitor binds to the allosteric site, so not where the enzyme and the substrate directly bind to each other. So it changes the enzyme's function or rate. However, the active site is unchanged. So you still have the same binding affinity for it, but so like the Km, like the su amount of substrate in order to reach one half of Vmax is still the same. But however, like that Vmax, for whatever reason, it's just like lowered for the non-competitive site. It's like not it like it's being fundamentally changed. Like it can't reach so it's like a runner, right? Um it's like when you're like running around, like you're doing like the mile, right? Like let's say someone has like you both have like the same your first lap is the same thing. So like think about that as like your cam. But like as you like if someone has like they had like better endurance. So like that one person was more or less a sprinter when they reached the same. They were like running as fast as they could. Whereas to reach that, let's say for example, like when you're running around a track, the first person, person one and two, they have a 45-second first lap. And this is would be equivalent to like the KM being the same. Whereas when they do their second lap, this person still has 45 seconds. Whereas this person two, since they were like sprinting, they were going as hard as they can. They don't have as much endurance. This is taking them a minute and 30. So it's less efficient. So that Vmax, its maximum rate that it can like do the reaction itself is lowered. That's sort of how you could think about non-competitive inhibition. And the same thing, so Vmax is different, Km is the same. So like Vmax is lowered. Um, and yeah, it's just more or less saying the same thing. Yeah. Yeah, and it's the same thing. So it's like you have a higher Y, so this would be the 50. This would be the inhibitor since everything is like opposite. It's like bizarre world. Um, and this would be regular, right? Since if you look at it, this is like 1/50th, and this would be like 1/25th. Oh my gosh, my handwriting is too big. This would be 1/25th. So like that 150 is less efficient. It's that sprinter. Um, and then my uncompetitive inhibitor. These are weird. So before I get into the Michaelis-Menten and Lou-Robert, once again, I'll kind of explain like what the heck is actually happening. So it binds to the enzyme substrate complex. So when they're ready, like bound to one another, and it kind of traps them in time for a little bit. It's like this weird intermediate state. There will they, won't they? Um, like break up, sort of. So it locks them together. The substrate is unable to like unbind, like so leave, so no product is able to form. But as a result, because like there's just like more of that enzyme bound to the substrate or the reactant, you are actually have a higher affinity for the the enzyme has a higher affinity for that substrate just because there's more of it locked together. So like that the Km is actually lowered for this. This is like the only one where it's actually better, I guess. So like the higher binding affinity here. Um yeah, whereas the Vmax, right? So like its function because it's like not able to form as much product, which is like kind of the whole point of an enzyme is to like do to create the product as fast as possible, which is your velocity or rate. So that will decrease. So you're decreasing the Km and the Vmax, but the Km is better to decrease it, whereas the Vmax is worse, right? So if you look here, this is the Michaelis-Menten. So you could see that for the inhibitor for that dark green, it's higher, right? So it reaches the KM way faster than your like just regular old no inhibitor reaction. Same thing here. So like think of the Lineweaver-Burke, they're parallel. It kind of like changes at like the same rate. Like increasing, decreasing. And it's the same thing. Whereas here the negative 1 over km, right? Since like this is a higher number, so like that negative 10, for example, versus negative 5. So if you do like 1 over negative 10, right? And then 1 over negative 5, like the 1 over negative 10, like yeah, negative 1. So this is like zero point 0.1 versus that zero point 0.2. This is more efficient, right? Since like you need less of that enzyme substrate in order to reach that 1/2 over the Vmax. So like you need less of it in order to produce the same amount of product. And yeah, that's kind of it. So like this is the weird one. Uncompetitive inhibitor, competitive inhibitors, and non-competitive. Those are the three types that you need to know for the MCAT. Hopefully that made sense. I apologize if it didn't, but yeah, enzyme kinematics can take a minute and to understand. But they're really, really, really important. That and the amino acids for biochemistry are the most important for the MCAT. So you really need to make sure that you understand this inside and out. And it's just easy points once you do understand. Well, once again, my name is Cha Cha. Hopefully that this made sense to everyone. And thank you for listening, and I hope you have a good rest of your day.